In this video, I'm going to talk over one of the homework problems here. I'm going to just talk over the key instead of rewriting everything because I think I would write the exact same thing. So just to help you understand what we're doing here, it says verify this solution. And the problem here with this solution in that DE, and we're so used to taking our solution, solving for y, making it explicit, and then plugging it into here, right? That's what we've been doing so far, is find, they gave us a y, we find the derivative, we plug it in, we verify it. That's not so easy here since this is an implicit equation with that squared. So what we could do instead is use what we called implicit, and this is from Calc 1, so this may be why it feels foreign, is we just take the derivative of both sides of that equation, which is what my first step is doing here. That's just derivative, right? Derivative of left side, derivative of the right side because it's a constant. The x term is nice and easy. It's a normal derivative, but the second is we don't know what y is, so we treat it like a normal derivative, but we also have to treat it like it's a chain rule. We don't know what y is. That's what we're trying to find, so that's why we tag on this dy dx. Right, and then it's just algebra from there. And what we're doing here is we did this derivative. We forced this derivative to be in our problem. And then what we're doing is we just worked it out with algebra to manipulate it to look like this problem here. Well, since I can take the derivative of our possible solution and manipulate it and make it look like our DE, that tells us it's a solution. It's just a different technique to verify. We use this when it's not so easy to make our solution explicit. Okay, so B says to graph it and then find all explicit solutions. So the graph of this thing, and it may be a while, in Calc 3 we did this. We do it pretty quick. Those of you that had me, especially with all this in the last semester, it was pretty crazy. We went through this pretty quick, but this is actually from, we do this in Calc 2, Sum 2, and before. This is a hyperbola. All right, how we graph hyperbolas is we put it in a standard form, and then this is our a squared, this is our b squared. That tells us the axes, and we get this like box here. And it's not going to be exact on here because of the numbers being off, and I just kept my numbers pretty straight. But this puts us in the x direction 1, our box, and then this would put it 1.7 in our y. It's totally off here, but a sketch is fine. I'm not going to ask you to sketch anything like this. But that is the solution. That is the curve that solves the DE if we were to graph it. They asked us in this problem, this is the curve, so it's just to find all explicit. We graphed it, this is what our solution looks like. The whole point I had you do this is I want you to understand we are literally finding solutions, or functions that are solutions. Not just a number, right? These functions have graphs and everything. We have this whole thing here. What we're going to do is, we're looking at this graph, we can see that it's only defined on certain intervals. And we're going to look at that here in a moment. But it's only defined from 1 to infinity on this side and negative infinity to negative 1. So we're going to have to consider which part of this solution would solve our DE. And that's what this whole next part is we can only find one open interval, one side of it. So to find all explicit solutions, this is turning this is implicit, right? And we're just going to solve for explicit. So we did that, right? We added the added the y squared over a minus 3. That's what we got here. Then we took our square root, introduced our plus or minus. Then we just started separating our square roots and factoring. From here, what we're doing is considering where we can plug things in. And what I did is, okay, so we want everything inside here to be greater than or equal to 0 because we can't take the square root of a negative. I didn't really show how that works out. What I do is I don't do very much algebra when I get to this part. I know some teachers would like do x plus 1 is greater than 0 and solve and all this other stuff, and I get really confused and I mess it up a lot, so I actually don't teach it that way. What I teach is I look for my zeros. Okay, that's negative 1 and 1. And then I just pick a number in my head and plug it in. So I always do, if I have it on there, I pick 0. If I plug in 0, I get a negative 1. Like 0 here, 0 here. I get 1 times negative 1. So that's negative 1 is greater than or equal to 0. That's not true. So I know to graph on the outsides. If it was true, I would just graph in the middle. One line in the middle. So that tells me that the domain of our function y, which we looked at our function, and we already wrote this down just a second ago, but this is our domain for that function. All right, so since we have these domains, we actually have different types of solutions because we have to say what the solution is defined on. We haven't been doing a lot of that. We've just been solving, and that's just because that's what I like to focus on in this class is the solving portion. The interval portion, so we want the interval to be open. That's just something that we always want it to be. So we keep it open. And what we do is we take the positive and negative and we define it on each one. So notice that the first interval we're doing is we did negative infinity, -1, right? We did 2 of those, right? We have the positive one, this is a positive, and we have the negative. So that's why we have 2 answers for that one. And then if you look here, we have 1 infinity and 1 infinity. I didn't mean to box that off earlier. And we have a positive and negative for that as well. So we actually have 4 different types of possible solutions. Now, if they don't give us an IVP and they just ask us to solve, none of this matters. It's a general solution. That's why most of the problems that we've done so far, we don't do a whole lot of this defined on the interval. So C says we want to determine which one would satisfy an IVP if we had the same problem and we had the initial condition y of -2 is 3. Well, if I look for this is x and y, and all our intervals are based on x. So I just have to find an interval that has -2. Okay, well, I have 2 different possibilities. This one has -2, and this one has -2. So now I just have to determine, is it the positive one or is it the negative one? Well, my answer, the y, comes out as a +3. Well, these will be negative every single time, right? We do all the square roots and then we'd have a negative. So it tells me that it has to be phi sub 1. So what we did in this problem, what you're actually finding is you solved or you verified. They gave you a solution. We graphed it just to remind ourselves that it's a function. We took that function, we determined its domain. We also took the solution, solved for the explicit solution, and now we have found that if it was an IVP, and that was the initial condition given, that our answer would be phi 1. Because that's where it's defined here. Negative infinity, -1 because of the -2, and then our answers are all going to be positive there, and that's what we want with our y. Kind of a confusing question, but it's actually, I feel like the wording makes it worse than it actually is.